All right, let's take a look at another CSES probability problem. This one is super complicated, actually. So, yeah, let's get into it. Just be warned. So we have a chessboard, and every square, it's 8 by 8. Every square has a robot, and they're all going to move k steps, and they're all sort of separate, right? They can go on top of each other. They don't depend on the other ones at all. And so they just move randomly, which I mean they just pick a direction, up, left, up, down, left, or right, equal probability, and they just do that k times. If you're at the corner, you can't move out the board, right? So if you're at the corner, you only have 2 options. If you're on the edge, you only have 3 options. And if you're sort of normally in the center, you have all 4 options. But among the options, it chooses randomly. And so the question is, how many squares are empty after k turns? Right, have 0 robots on them. K is from 1 to 100, and that's the only input. And yeah, so if k is 10, then the answer is 23, which is not at all obvious, at least to me, but sure. So yeah, how do we do this? It's complicated, as I mentioned. Here's my write-up of the solution. So first I need to tell you about some probability concepts that we need to solve this problem. Right, so we want the expected number of empty squares. So what does expected mean? So suppose we have some random variable, which just means something that can come out in different ways, right? Like the throw of a dice is a random variable, takes on values 1 through 6. In this case, the number of empty squares is a random variable, which can be anywhere from 0 to 64. Well, I guess it can't be 64 because the robots have to go somewhere. 0 to 63 then. So that there's various outcomes that it could have and various probabilities of those outcomes. So the expectation is just the average value, right? That is a weighted average of the outcomes according to their probability. So it's just this. So a key fact, both in general and probability, and for the solution to this problem, is linearity of expectation, which just says that you can add averages, right? The average of x plus y is just the average of x plus the average of y. So here's a proof of that. I don't think I really want to go through it, but I don't know. You can look at it, I guess, and convince yourself. But right, so x, I guess this maybe was saying, what do I mean by the average of x plus y? Well, that is the random variable, which takes on the value x, xi plus yj, right, some specific values, with the probability that we actually get those values. So this is not like a totally trivial statement, right? You want to prove that this thing is equal to this thing. But it's not trivial, but it's not very difficult. Right, the point is that you can just separate out x and y from these sums, and then it will turn out that the x part is just d of x and the y part is just d of y. Okay, so that's the first concept, is expectation and linearity of expectation, right? That you can add, a sort of addition commutes with e, with the expected value. Okay, so the next concept we're going to need is of an indicator variable. This is just an idea that you can use that's often useful. So an indicator variable is just 1 if some event happens and 0 otherwise. And the point is that the expected value of the indicator variable is just the probability that that thing is true, right? Because you get 1 if the thing is true and 0 otherwise. So, okay, so we can use these two concepts of breaking down what we want into a sum of indicator variables to help solve the problem. But what we want is the expected number of empty squares. So we're going to define an indicator variable for each square for whether or not it's empty. And then the number of empty squares is obviously just the sum of those indicator variables, right? If we count 1 if the first square is empty, 1 if the second square is, and so on. So this is just another way of writing that. But that means that the expected value of the sum of the empty squares by linear expectation is just the sum of the expected values of all of the indicator variables, and that's just the sum of the probability that all those squares are empty. So this is an important sort of simplification. We've gone from finding the expected number of empty squares to finding the sum over all the squares of the probability that that square is empty. And those, that's the same thing. And the reason for that is like all of this stuff. right? In particular, this argument about indicator variables. And this is indicator variables in linear expectation is like a pretty useful probability trick, so it is worth understanding that, I guess. Okay, so but how do we actually do it from here? So we need to find the probability that all the squares are empty. So a square is empty if there are no robots on it at k steps. So maybe we can find out the probability that each robot goes to that square. So let's say that we could do that. We'll call that pk from AB to RC is the probability that if you started on AB, then you end on RC after k steps. And so 1 minus pk AB RC is the probability that you don't go to RC. Right, negating a probability is 1 minus. And so if it's only empty if they all fail to land on RC, and the probability that they all don't land there is just the product of the probability that they each don't land there. And here's where we're using the fact that the robots move independently. Right? If two things are independent, that means that the probability that they both happen is just the product of the probability that they each happen. That's like the definition of independence, I believe. Okay, so the probability that RC is empty is just the product over all possible starting squares, starting robots, of the probability that that robot does not move to this square. And so our answer is just going to be the sum of all the squares of that product. Okay, so how do we compute pk? Matrix exponentiation, actually. So this is very similar to the graph sort of adjacency matrix stuff that we've been looking at. So let's see like what it looks like here. So let P of AB RC, so P instead of PK, be the probability that we go from AB to RC in one step. So this is actually very easy to compute, just like based on the chessboard, right? You just like write down like the neighbors of each square, right? So like each corner has 2 neighbors, so you write down, you know, that the corner has a half probability to go to each of its 2 neighbors. And you know, the same thing for the edges and in the interior squares. So this is basically just writing down like the adjacency matrix, except we're writing down probabilities instead of edge weights, but you know, it's fine. And then it will turn out that p to the k, right, so the matrix exponential of this adjacency matrix of AB RC is the probability that we go from AB to RC in k steps, right? So p, 1 step, pk, p to the k in k steps. And it's basically the same argument as the like other graph adjacency matrix exponentiation stuff we've been looking at, but just to recapitulate it in this context. So the sort of general case is if we have a product of 2 powers of p from AB to RC. So just the definition of matrix multiplication is that it's this, right? It's the dot product of the AB row of A with the RC column of p to the b. But we can also interpret that sum as brute forcing over the middle vertex, right? So the probability of going from AB to RC in A plus B steps, well, after A steps, you must be somewhere. So for all of those somewheres, the probability of getting to RC going through that K is just this, right? Because it's all independent. So this is the probability that you got to K in A steps, and this is the probability that you got from K to RC in A plus B steps. And so this is the probability that you got from AB to RC in A plus B steps going through K, and you must have gone through some K. So this is the probability that you went from AB to RC in A plus B steps at all. So let's put that all together. Right, this big screen of text. First, we write down P, just based on like the chessboard, right, as the adjacency matrix. Then we can use matrix exponentiation to compute P to the K, and then we can compute the answer, which is the sum over all the squares of the product, you know, of these particular values in P of K, which we got from linear expectation. So that was a lot. Let's actually do it. I think the code will not be as long as the explanation. Actually, we don't even need to be in K for a while, right? We can just. This problem is kind of weird in that it has very little input. So I'll use either stream. We need vector namespace stud 64-bit int, and we're also going to use doubles, as I guess is probably typical in probability questions. So P is going to be a matrix of doubles. 8 vector LD 8. We'll say P is a mat. Starts at 0. It's actually not 8. Right, there's 64 squares in an 8x8 chessboard. And P kicks us from squares to squares, so it should be 64 by 64, not 8x8. So we're going to build up a list of neighbors. So there's 4 directions, which I like to use this sort of system for directions. I'll explain what this means. So direction 0 is going to be up, which means you go -1 rows and 0 columns. Direction 1 is right, 0 rows, 1 column to the right. Direction 2 is down, so that's 1 row down, 0 columns. And direction 3 is left, which is 0 rows and 1 column to the left. This is R plus dr for this direction, C plus dc of this direction. Okay, and we want to check if this is in bounds. Okay, and we need to, so we want to represent a single square as like a number from 0 to 63, not as a pair. So we will just do R times 8 plus C to do that. So for each of, so this is computing your neighbors. This is the check if you would go out of bounds. And then the probability that you go to each neighbor is just 1 divided by the number of neighbors. Okay, so that's P. Now we actually need to read in K. And now we can just compute the answer. RC. And we want to print out 6 decimal places, which you can do with fixed set position 6, which requires the IO manip header. Okay. Yes, we actually need to define matrix exponentiation. First we need to define matrix multiplication. A dot size, vector LD 0 dot size 0.0. No mods or anything like that because we're doing floating point. These are floating point integers. There's no overflow. And anyway, they're probabilities, so they're between 0 and 1. Okay, now we want map pow. So this is just the usual. Again, explanation by squaring, amazing. Although we actually probably don't need it for this problem because k is only up to 100 for some reason. Right? We could have solved this with k up to like 1 billion. It would have been exactly the same solution. So I'm not sure why they didn't ask for that. Okay. 61 is not correct. All right. Expected number of empty squares. That's not good. Corner seems to have 3 neighbors. So what did I do wrong? Not D, but R. Okay, that seems important. Other corner has 0 neighbors. The thing you passed the direction is D. Lots of dumb mistakes here. Okay, RR is R plus DRD, C, C, yes, fine. Okay, this looks much more sensible. That's still wrong though. Doesn't seem right. So many dumb typos. The neighbor is not our column, but the other column. Three. Let's see. The probability he does land on us is 1/3. So the probability that no one lands on us is 2/3 times 2/3 is 4/9. Sure. One, 207. Isn't that wrong when I had all the debug statements turned on? Oh, okay, guess I was right. Cool. So turn off all the debug. 23.120740. Moving robots. Cool, so it works. A little more debugging there than usual. I guess I'm off my game with the grid stuff. I think like all the bugs are in here. But anyway, yeah, so complicated solution. I mean, this stuff is all sort of just general background knowledge that you should know about probability, right? This is very important, and this indicator variable method is quite useful for. This is a good example of a problem where it's useful, right? So we apply it to this problem. We figure out that we just want the sum of these probabilities. Then we figure out to get the probability that it's empty, we need to figure out the probability that each robot ends up on it. Realize that this is like a counting the number, not really the number of paths, but the probability of a path from A, B to RC in k steps. Make the connection to matrix exponentiation that we saw earlier, and then put it all together. And I guess also realize how to combine, the probability that the square is empty means the product of the probabilities that each robot doesn't land on it. So yeah, the code is actually not that bad, right? This is the matrix exponentiation code. Very general. This is like the chessboard specific, like adjacency matrix code. And then this is just getting the answer. So, that's each of these steps, right? Computing P, matrix exponentiation, and then getting the answer. So the code, not that bad in the end, but kind of a complicated problem using, a couple different ideas, a couple different steps. So hopefully you thought that was cool. And the takeaway here is the linearity of expectation indicator variable thing. That's what's new in this problem.